Okay, so hello everyone. Welcome to another interesting session of the Astro Club. So today we are going to learn a new topic, that is pulsars. So the new topic that we're going to learn today is pulsars. So we'll be discussing how the pulsars were discovered and what are the properties of pulsars and all the complete information related to pulsars. So pulsars are the lighthouses of the universe. But what is a lighthouse? We should first understand what a lighthouse is. So here in this picture, left-hand side, you can see this is the lighthouse. A lighthouse is a high tower equipped with a bright light. See, this is a bright light and lenses. Here on the top of the light tower, you'll be having the lenses that help guide ships to the port at night and also alert the sailors about the sandbars, reefs, and rocky coastlines. So mainly, this lighthouse is mainly useful during the night for the sailors who sail in the seas. Okay, it warns them about sandbars or any rocky coastlines which are approaching in front of them. Okay, so this is a lighthouse. So pulsars are considered as the lighthouses of the universe. So pulsars are very much like lighthouses, but unlike the terrestrial lighthouses, pulsars can send out beam of X-rays, radio waves, and gamma rays. So normally the traditional lighthouses or the terrestrial lighthouses, what do they emit? They emit the normal light. See in this figure, you can see normal light. But whereas the pulsars keep on sending out X-rays, radio waves, and gamma rays. Okay, so did you all understand this slide?
Yes, sir.
Yeah.
Yes, sir.
So before we get to know about pulsars, it is very much important to know about the discoverer of pulsar. So it is none other than Jocelyn Bell. So she was the one who discovered pulsars. And also there's a very interesting story about how she discovered pulsars. The story is very interesting. So now I'm going to tell you that story. You'll definitely enjoy that story.
Akka,
Yeah.
she is a boy or a girl?
Girl only. She's a girl. Jocelyn Bell. Okay, she discovered pulsars. So here is an interesting story about how she discovered pulsars. So let's see. In the year 1967, Jocelyn Bell was a graduate student at Cambridge University. So she was a graduate student at the Cambridge University, and she was working on her thesis about strange objects in the distant galaxies known as quasars. So actually, she's doing the research on quasars. We have discovered quasars. We have discussed quasars in our previous session. Do you remember that?
Yes, sir.
Yes,
Yeah.
sir.
So this Jocelyn Bell, she was mainly working on quasars. She and her supervisor have built a radio telescope to discover them or to observe them. So in order to observe the quasars, Jocelyn Bell and her mentor and her supervisor, they had built a radio telescope. So this is how a radio telescope looks like in the left-hand side. So first I'll explain you what a radio telescope is. So a radio telescope is an astronomical instrument consisting of a radio receiver and an antenna system that is used to detect the radio waves emitted by the extraterrestrial sources such as stars, galaxies, and quasars. So mainly this radio telescope, it consists of a radio receiver, and also an antenna system. So what is the use of the antenna system? The antenna system is used to detect the radio waves which are being emitted by the distant objects, extraterrestrial sources. It can be stars, it can be galaxies, or it can be quasars, anything. Okay, so if you observe this picture on the top right corner, So from the extraterrestrial sources, the radio waves will be coming like this, and this is a dish reflector. As soon as they fall, as soon as they fall on the dish reflector through the cable, those signals get transferred to the amplifier, and via the amplifier, those signals again get into the computer. So data from the telescope was scrolled out from the computer. So from this telescope, finally the data goes into the computer. So finally what happened? She scrolled out the data from the computer. She took the data from the computer, and as she poured over the data, she noticed something strange. As she was looking through the data, she noticed something strange. What is that strange thing she noticed? It is an unclassifiable squiggle. It indicated mysterious radio waves pulsing repeatedly. So if you see this figure, initially they were all like a straight line. But after some time, a squiggle appeared. Squiggle in the sense up and downs. And they were coming rapidly.
Yes.
Yeah, it was uneven. So these were the mysterious radio waves noticed by Bell. So as she was looking through the data in the computer, she noticed these mysterious radio waves. Okay, so she took more data from the telescope and brought the results to her mentor, Hewish. So this is Hewish, Bill's mentor or Bill's professor. So she took more data from the telescope and she collected all of that data, and she took that data to her mentor, Hewish. Initially, they thought these interferences are artificial or man-made. At first, they did not believe about her observations here. They all thought, okay, these interferences, like all these things, they were mysterious or they were man-made, they were artificial, they thought like that. But soon it was ruled out after observations with another telescope. But what they did later with another telescope, they observed it again. So they nicknamed these signals as little green men, in a notion that these signals were for aliens. So they did not know that they were pulsars. They thought they were some little green men from other galaxies, and they thought that these signals, these radio signals were coming from aliens. Okay, and they nicknamed these signals as little green men. Okay, did you all understand till here?
Yes, sir.
Yeah. But finally, it was noticed that the radio waves were coming from something moving at the same speed as the stars. But later, what happened? Finally, they noticed, what did they notice? Like these radio waves were coming from some objects. Like they were moving with the same speed as the stars. So from those objects, these radio waves were coming, they noticed. So these objects were responsible for the squiggle. So finally, it was confirmed that those objects were responsible for this uneven movement of radio waves and the squiggle. And now we are calling those objects as pulsating stars or simply pulsars. So that is how pulsars were discovered. Okay, so this observation is considered as one of the greatest astronomical discovery of the 20th century. So this is really amazing discovery by Bell, Jocelyn Bell. So this is her mentor, Hewish. Okay, but here we get a twist in the story. So Nobel Prizes were being awarded at that time. And you know who received the Nobel Prize? Can you guess who received the Nobel Prize?
I think, I think it's Hewish.
Yeah, that's true. Actually, who discovered pulsars? Bill discovered pulsars.
Bill.
But it was her mentor, Hewish, who received the Nobel Prize in 1974. Why did Hewish receive? Because in those days, the students weren't recognized by the committee. The Nobel Prize committee did not recognize the work of the students. They were only giving the Nobel Prizes to the professors or the mentors. So Hewish became the first astronomer to be awarded the Nobel Prize in Physics at that time. Okay, it was Bell's discovery, but Hewish received the Nobel Prize in 1974. Okay, did you understand till here?
Yes, Akka.
Okay, so now coming to our main topic. This is all about the discovery of pulsar and getting the Nobel Prize and just the introduction. Now we are coming to our actual topic. What is pulsar? We'll be discussing about what is pulsar. So basically pulsar is a neutron star. Just a second. Yeah, so pulsar is a neutron star. So a pulsar is a type of neutron star. The formation of pulsar is very similar to the creation of a neutron star. Like how a neutron star is created, in the same way pulsar is also created. So it's a type of neutron star. Neutron stars are formed when a massive star runs out of fuel and collapses. When a massive star, it runs out of fuel and it collapses, then a neutron star is formed. So the very central region of the star, that is the core. So what is the central region of any star? The core is the central part of any star. So the core collapses, crushing together every proton and electron into a neutron. So the entire core gets collapsed and all the protons and electrons gets combined together into a neutron. So imagine such a big massive object when it gets crushed down and when it gets broken down or when it gets squeezed. So all that enormous energy and all the enormous mass will be concentrated in a small size. Okay, so if the core of the collapsing star is between 1 and 3 solar masses, these newly created neutrons can stop the collapse, leaving behind a neutron star. So that is how a neutron star is formed. And pulsar is a type of neutron star because it also gets formed in the same manner. So the next interesting topic we're going to learn is stellar life cycle. So what is the main life cycle of a star or the stellar life cycle? Let's find out. So the most massive stars detonate as supernovae. Detonate meaning is burst out. So many massive stars, they burst out as supernova. We know that, right? And they can explode or collapse into black holes. So they can even collapse into a black hole. If they are less massive like our sun, they blast away their outer layers and then slowly cool down as white dwarfs. So this is our sun. Our sun has low mass. So here a very important point you need to understand. If a body has low mass like our sun, then finally it will turn as a red giant and finally it turns as a white dwarf. If it has high mass like the neutron star or like the pulsar, it will finally turn out as a black hole or a neutron star. If it has a low mass, it turns out to be a white dwarf. If it has high mass, first it will turn as a red giant in both the cases, and finally it can turn either as a black hole or a neutron star. So, but for stars between 1.4 and 3.2 times the mass of a sun, they may still become supernovae, but they just don't have enough mass to make a black hole. Okay, so these medium mass objects end their lives as neutron stars, and some of them can become as pulsars also. So if they have the medium mass, then they end their lives as neutron stars, and some of them can become pulsars also. So is this clear? Is this slide clear?
Yes, sir.
Yes, sir.
Yeah. Now, so pulsars are the most dense objects known, and an object with the mass of a sun squished down to the size of a city So pulsar is nothing but like it has a mass of a sun and now it is squished down to the size of a city. So these stellar corps emit intense beam of radio waves from their poles and therefore they're called as pulsars. So see here, see this slide. This still from an animation shows an artist's impression of a pulsar. See, this pulsar is surrounded by strong magnetic field lines, the blue lines. See, all these blue lines are strong magnetic field lines and emitting a beam of radiation, that is purple color. This purple color is a radiation which is being emitted from this pulsar, and these blue lines represent the strong magnetic field lines. Okay, that is about this one. Now comes an interesting topic. What if a tablespoon full of neutron star is brought onto Earth? So from that whole neutron star, what happens if you bring a small teaspoon full of neutrons? See this picture. If you bring a teaspoon full of neutron star onto Earth, what will happen? So a tablespoon full of the sun. First, let's consider about the sun. If you bring a tablespoon full of the sun, depending on where you scoop, it would weigh about 2 kgs, the weight of an old laptop. So if you bring a tablespoon full of the sun, it weighs just 2 kgs, like the weight of an old laptop. But if you bring a tablespoon full of neutron star, it weighs more than 1 billion tons, which means 900 billion kgs. See, that is the weight of Mount Everest. So 1 teaspoon or 1 tablespoon full of neutron star is equal to the weight of Mount Everest, 900 billion kgs. So imagine how heavy it is when compared to the sun. Neutron star is very heavy when compared to the sun. So while you can lift a spoonful of sun, you can't lift a spoonful of neutron star because even small amount of neutron star weighs 900 billion kgs. But whereas a small amount of sun weighs only 2 kgs. So just get to know the weight of neutron star, how heavier it is when compared to the sun. Okay, did you all understand this slide?
Yes, Akka.
Okay.
Yes, Akka.
Yeah. Now moving on to the structure and mechanism. So when a star collapses into a neutron star, radius is dramatically decreased to a fraction of original star, to a fraction of the origin star or original star. Because when a huge amount of star, when it gets decreased in size, what happens to its radius? Radius also gets decreased. Okay. And neutron star can spin as fast as 43,000 times per minute. See, it keeps on spinning like this, 43,000 times per minute, and gradually slowing over time. And as the time passes, it gradually slows down and its life ends someday. But it may take many years. But initially, it spins 43,000 times per minute. However, the axis of the magnetic field is not aligned with the neutron star's rotation axis. So if you observe this right side picture, this is a rotation axis, which is in the middle, the red color line. And this is the radiation beam, this yellow color line. So if you observe, the rotation axis and the radiation beam will never meet. Like they are not aligned with each other. Okay, this one is in one direction and this one is oblique, in oblique direction, the radiation beam. So they never align or they never meet with each other. The magnetic field of the average neutron star is about trillion times as strong as Earth. We know, right? Earth has a strong magnetic field. But in the neutron star has magnetic field which is trillion times more than Earth, which is trillion times as strong as Earth's. So just imagine the power of neutron star.
Means more stronger than Earth.
Yeah. More stronger magnetic field than Earth. So what can we conclude? The combination of strong magnetic field plus rapid rotation produces powerful electric field. Okay, strong magnetic field plus rapid rotation. It has strong magnetic field and it rotates at a greater or higher speed. Then what? comes finally, powerful electric field is generated finally. And a single cubic meter of magnetic field in a pulsar contains more energy than humans have generated till date. So first you should understand what is cubic meter. Cubic meter means like the length of each side of a cube, which is 1 meter long. So a cubic meter of magnetic field in a pulsar means if you take small amount of magnetic field in a pulsar, how much energy it contains until now, how much electrical energy humans have, until now how much energy that humans have generated, it contains more energy than that. Okay, did you all understand?
Yes,
Yes,
Akka.
sir.
Yeah, so that is all about pulsars. I hope you have understood. So now let's watch a video so that you can understand it much better. Is the screen visible and is it audible?
Yes, sir.
Okay.
Yes.
A pulsar is a rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star.
See, it keeps on spinning like this.
A teaspoon of matter from a neutron star weighs as much as Mount Everest, and a neutron star is so compact that a ball about 15 miles across contains more matter than our sun. Neutron stars spin between 7 and 40,000 times a minute and form with incredibly strong magnetic fields. Rapid spin and intense magnetic fields drive powerful beams of electromagnetic radiation, including gamma rays. As the pulsar rotates, these beams sweep the sky like a lighthouse. To a distant observer, the pulsar appears to blink on and off. Pulsars slow down as they age, but some of the oldest pulsars spin hundreds of times a second. Each of these millisecond pulsars orbits a normal star. Over time, the impact of gas pulled from the normal star has spun the pulsar up to incredible speeds. This accretion may be the cause of their weaker magnetic fields. Despite this, these pulsars also emit gamma rays.
Yeah, so that is the video about pulsars. Did you understand?
Yes, sir.
Yes, Akka.
Yeah. Okay, so this is all about pulsars. And one more thing, I just wanted to inform you. Maybe next session, we'll be having a Kahoot quiz. Like, I don't know if it's confirmed or not, but most probably I'm planning for a Kahoot quiz next session. Next Sunday, we'll be mostly having a Kahoot session. So you just need to revise the earlier concepts, right? So as you know, I've been uploading all the session recordings in my YouTube channel. You know my YouTube channel link, right? So
Yes,
if you,
sir. We subscribed also.
yeah, okay. So if you want to revise the concepts, already the recordings are there in that channel. So you can just watch those videos so that all the concepts you'll get a revision, and then you'll be able to do well in the Kahoot quiz in the next session. Okay. So whenever you have time, just go through those videos.
Okay.
Yeah. And also one more thing, after few sessions, I'm planning for some hands-on activities. Hands-on activities in the sense, one day before the session, I'll inform you what materials you need to bring. Some craft materials, like that I'll inform you. Okay, so that if you be ready with those materials, then we can do some hands-on project or hands-on craft activity in the class, in the session, okay? Yeah, I'm planning for that, and
Okay.
I'll inform you what materials you need to bring. Not now, maybe after a few more sessions, but for the next session, mostly be ready with the Kahoot quiz.
Okay, Akka.
Yeah. Okay, so that's all for today's session. Thank you for joining. You can leave.